Okay, so again, this is Form A from yesterday's quiz over kinetic energy, work, and power. We're just going to go through it one at a time, all 16 questions. And again, you should expect the multiple choice section of tomorrow's test to look similar. So it would be a good idea to jot down any of these, especially ones that you had issues with. It would be a good idea to have those written down so that you don't make the same mistakes tomorrow.
Ms. Darwin?
Yes.
There's also going to be a video for this, right?
Yes, I'm recording it right now. Okay, so question number 1, you guys overall did really well on. The campus average on it was an 85%, and it says, a hockey player wishes to do work on a hockey puck sliding horizontally on the ice. Which scenario would yield the most work done by the hockey player if their stick is in contact with the puck over the same distance? This question is really just asking us how the angle at which the force is applied affects the work that's being done. And we've looked at that. The closer that angle is to 0, where it is parallel and in the same direction, the closer you are to 0, the more work you're going to do. And you can kind of picture those triangles, because as those angles get smaller, the horizontal component of your triangle gets longer and longer. And so you just want to pick the one closest to 0. And that's going to be answer choice D. And as I said, almost everybody got this one right. Those of you that missed it went the wrong direction and went with the largest angle. If you picked one in the middle, that doesn't really make much sense. So really A or D were your main choices to look at. But again, if you have a 15-degree angle, if this is your horizontal, 15 degrees is a really small angle, something like that. And when you look at the components of that triangle, this horizontal component is obviously long in comparison to the vertical. When you're at 60 degrees instead, and again, I don't have a protractor, but obviously this is a much bigger angle. Now this horizontal component is shorter in comparison, and the vertical is longer. Okay, so you're looking for the one with the largest horizontal component because that's parallel to the direction of your motion and the closest to 0. If 0 was a choice, pick it. Okay, but the closer you are to pushing perfectly horizontally, the more force you have that's doing work. Okay, so we've seen that over and over again, but number 1 was D. All right, number 2. Numbers 2, 3, and 4 all go with this graph in this scenario. The scenario says a ball is thrown downward from the roof of Bridgeland High School for a physics experiment. The bar chart to the right shows the energy of the ball at 2 different points in time during its fall. Assume the ball is in free fall so that there is no air resistance. Question 2 says, based on the data given, what is the net work done on the object? Again, net work is equal to the change in energy for your object. Okay, so when you look at your bar chart, you can see the initial amount of energy and the final amount of energy. And just based on that alone, this is a positive change. You can eliminate half of your choices. Don't pick a negative work as one of your options. Okay, you don't want to pick A or B. They don't make sense. If you had A or B, then this bar should have gotten shorter because these represent a loss in energy. So right off the bat, you can eliminate half of them. You're really just choosing between C and D because those two are positive work. And in my graph, I have more work at the end than I started with. Or sorry, more energy at the end than I started with. Okay, so it is a positive change. And all you have to do is read the values over here. You started with 10, you ended with 20. So my change, again, final minus initial is how you calculate that. 20 minus 10 is 10. It's positive 10. And so the answer you should have for number 2 is C. And again, most of you got that. 76% of you got that one right. But yes, it's C, positive 10. Number 3. Okay, number 3 says, if the ball has a mass of 149 grams, how fast is it moving at the final point shown in the graph? Again, it's telling you to look at the final amount, which was 20 joules, and to use that to calculate how fast it would be going. This is 20 joules of kinetic energy. That's what the label says. Okay, and so you can just plug this directly into the kinetic energy equation. That's this equation here. KE equals 1/2 mv squared. And when you substitute your values in, your KE is equal to 20, because again, that's the final amount on your graph, equals 1/2, and then you need your mass, but your mass needs to be in kilograms. This is in grams. So if you missed this, that's probably why. there are 1,000 grams in a kilogram. So if you have 149 grams, that's not even 1 kilogram. It's a fraction of that. Okay, specifically, divide by 1,000, you'll get how much it is. It's 0.149 kilograms. And then multiplied by v squared. And that's what we're trying to solve for, is that velocity. So from here, we would need to move everything over here. Okay, so 20 divided by a half is the same thing as 20 times 2. Okay, and then we'll divide by 0.149. Okay, and this is what I get when I do those two things, 268.456. But again, that's equal to v squared. So you still have to take the square root of this value. Okay, some of you were asking me where the square root button was yesterday. Guys, y'all need to be doing your practice problems with the same calculator you're using on the test. You should not be asking me how to use the calculator when you're taking a test. Okay, so here's where it is. You're going to press the control button because the square root's right there in gray. If you see it, it's next to the 4 above the squared. It's right there in gray. The control button is how you access those. Okay, there's your square root. And I want the square root of, and this calculator's being weird, 268.456. And I get this. Okay, 16.3846. When I look here, that's going to be 16.4. That is answer choice D for number 3. All right, for number 3, a little over 2/3 of you got it right. So again, it wasn't a heavily missed question, but it was one that about 30% of you missed. All right, number 4 also goes with this graph. And number 4 might be, no, it's not the most missed, but it is, I think, the second most missed. It is. Second most missed question is this one right here. It's not even math. Okay, it's a concept, and a lot of people missed it. In fact, only 40% of you guys got it right, which means 60%, over half of you missed it. It says, which of the following is or are responsible for the work done on the ball during its fall? And the word during is even underlined to point out that I mean while it's falling. Okay? While it's falling, if it's in free fall, and it says it right here, it's in free fall. The only force acting on an object in free fall is gravity. That's it. I know it was thrown before it was falling, but while it's falling, the only force doing work on it is Earth's gravitational field. Okay, if I asked for when it was being thrown, then yeah, the hand is going to be applying a force to it when it's being thrown. But once it's no longer in contact with that hand is no longer applying a force to it, and that hand is no longer doing work on it. Okay, so the answer to number 4 is A. The most common wrong answer here was C. A lot of you thought it was both gravity and the person who threw the ball. But again, that person who threw the ball only does work when the ball is in their hand, when they're applying a force to it.
Gravitational force is
it's just that one. Yeah, that's what we said. Okay, so that's number 4. Let's look at number 5. Number 5 is a calculation that involves an angle. Okay, it says you pull your friend in a sled with a constant force of 102 newtons at a 30-degree angle with respect to the ground. You pull for a distance of 57 meters. How much work did you do? Ignore friction. Okay, again, this is just that work equation. And when you have an angle, remember that you do need to take that angle into account. We wrote the equation like this. Work equals FD cosine theta, and the reason we have this cosine theta in there is because only the horizontal component of the force is doing work. So when you multiply this force times this cosine theta, you're finding that this piece right here. That's what you're finding when you do that. And then you multiply that by the distance. And you can do it in steps or just go straight to that equation. Okay, so when you plug in here, now first things first, you do need to make sure your calculator is in degree mode. If you did this in radians, then yeah, you're going to have a problem. Okay, if you look at the top of the calculator, it'll say DEG next to the battery indicator if you're using one of the Inspires. If it says RAD, you will need to switch it to degrees. This one's already in degrees, so I don't have to switch anything. Okay, for this, we're just going to multiply the force, which is 102 newtons, multiplied by the distance, which is 57 meters, and then multiplied by cosine of my angle. And again, to get cosine, you're going to use the trig button. okay, which is right here next to the number 7, and we want cosine. And this calculator, I think I have to grab a different one because this one won't, the keypad isn't working. So hold on, let me grab a different calculator. Figure out what's wrong with that one. Okay, sorry about that. So let's go ahead and take a look. Okay, so again, we're in degrees. It's right there. And so we're going to do 102 times 57 times cosine, okay, of, what was the angle? 30 degrees. Enter. Okay, so 102 times 57 times cosine 30, it should be this value right here, 5,035.07. It's rounded to a whole number here, 5,035. But the answer for number 5 should be B. And 88% of you got this one right, so you guys remembered that. You did pretty well with it. Okay, all right. Number 6. Number 6 has this scenario, and it tells us to use it for the next 2 questions. So the second part of it's actually on the next page. But it says, an 8-kilogram box pushed from rest is pushed from rest with a force of positive 50 newtons for 0.5 meters across a horizontal surface. Ignoring friction, what is the final kinetic energy of the box? Okay, so initially this thing is at rest. It is moving at the end, and the only reason it's moving is because there's work being done, and that work is equal to the change in kinetic energy. Okay, and you could write out that energy equation. Remember we said initial energy plus work equals final energy. That's the equation you could use as well. It's the same thing as this though, just rearranged. But my initial energy is 0 plus the work would equal my final energy. Okay, and I can get my equation from there. Okay, again, because the initial is 0, if I subtract it and I have final minus initial, that's this. So if you want to write it this way, you can, and you can just write KEF minus 0. It's the same thing, just rearranged. I don't really need the 0, so I just know that the work done is equal to the final kinetic energy. Again, I'm looking for what that final kinetic energy is, so I'm not actually looking for how fast it's going. Sometimes they ask for velocity. Don't find that here. It's not asking for it. Okay, you don't need to find that here. Instead, you just need to figure out what the work is and then use that to find your KE. And work, again, is force times distance times cosine of your angle. In this case, there's no angle, so it's just force times distance. The force is 50. The distance is 0.5, and that will be equal to my final kinetic energy. That's all you had to do. Okay, so 50 times 0.5, half of 50 is 25 joules. The answer to number 6 should be A. 80% of you guys got this one right, so most people figured out how to do that. But if you're forgetting it, you have to be able to write your own equation. This equation's not on the sheet. You have to know how to write your equation based on the scenario. Okay, so you might want to go back and look at that if you had trouble with that question. All right, let's look at the second part that goes with that scenario, which is right here. It says, if friction is present on this surface, which statement or statements correctly describes this scenario? So again, we have a scenario where there's a box being pushed from rest and then it's moving. Okay, that was what was described. Okay, so the first statement says the final kinetic energy of the box is less when friction is present than without it. That's true. Okay, if friction is present, it won't be moving as fast, right? And that's what this is saying. Okay, so if there was friction present, then yeah, this would be true. We want statement 1 in our answer, so I know it can't be C. Okay, the other ones all have statement 1, so we need to keep reading. The next statement says the friction does negative work on the box. Okay, again, friction applies a force that is always opposite the direction of the motion of the object. That will do negative work because the force will be in the opposite direction as the displacement. And you can also think of the fact that it makes it slower than it was supposed to otherwise be. That's a negative change in energy. So you can think of it either way. But yes, statement 2 is also a true statement. So we definitely want 1 and 2, so I know it can't be A. I now am choosing between B and D. Statement 3 says the net work on the box must be 0. Now that's not even in either of these statements, so I already know it's not true. The net work could be 0. It is possible that the friction matches the force that's being applied, but it's not required. Okay, it is possible to have less friction than whatever the applied amount is as well, so you don't have to have, again, this is the problematic word must, you don't have to have it where it's 0. Okay, so statement 3, not correct. Okay, statement 4, gravity does negative work on the box. Again, if you were to think of the forces acting on the box, gravity is a downward force. However, the box doesn't move vertically. The box is moving horizontally. Gravity is perpendicular to the direction of motion. And we said that anytime our force is perpendicular to the direction that it's moving, it's not doing work. So gravity does not do work here unless the box was moving vertically. Okay, it's not. So gravity's not doing any work, which means the answer to this is just statements 1 and 2. That's answer choice B. Number 7, about 2/3 of you guys got this right, which means about 1/3 of you missed it. So the most common wrong answer was D. So that's good. You at least identified 1 and 2 were right. You just had trouble with this statement here. But again, if you have a vertical force and no vertical displacement, that vertical force is not doing any work. We've looked at that example with somebody carrying something. Okay, we've talked about that over and over. That's not, you're not doing work.
If you weigh something, you do work.
If you raise it, yes, because then it's moving vertically. But if you're carrying it, no.
Horizontally, no work.
All right. Number 8. A roofer climbs a ladder carrying a 3.6 kilogram box of roof shingles. Okay, so this one, vertical. Okay, now that is going to be work. Okay, so this one is not going to end up being 0. If you put 0, sorry guys. Okay, but he's carrying this box vertically, so he's lifting it along with his own weight. If it takes him 17 seconds to carry the box up the ladder from the ground to the roof 5.2 meters above, how much work does he do on the box? Again, work is force times displacement times cosine of your angle, but I don't really have an angle here. It's in the same direction. He's lifting, he's applying an upward force, and he's moving up. So there's no angle to consider, and it doesn't tell me that there is one either. So it's just going to be force times displacement. If you are lifting something or carrying it up a ladder, same thing. The force that you have to use is the weight of the object. Okay, so the force you have to use anytime you're lifting something, even if it's your own weight because you're climbing stairs, same thing. Okay, the force you have to use is Fg. Okay, so Fg is mass times Earth's gravitational acceleration. They give me the mass. I just have to multiply that mass times 9.8, and that's the force I need to use. Because they don't tell me the force. But again, and you write this down so you don't miss it tomorrow in case it shows up. If you are lifting something, okay, the force you're using is equal to the weight of the object. So multiply the mass in kilograms times 9.8. Okay, so let's go ahead and do that. Mass in kilograms here is 3.6. So 3.6 times 9.8 means that the force used to raise this thing is 35.28. Okay, so that's my force. I'm looking for work. Okay, so 35.28, and then times the distance. The distance he's traveling, his vertical distance is right here, 5.2 meters. So that's all you have to do is multiply the weight of the object times 5.2. I don't need the time. I know they gave me a time. I don't need it. That's not part of this calculation. Time doesn't show up in the work equation. It does show up in the power equation. So if I had asked for power, the time would be relevant, but not for this. Okay, when I multiply the weight of the object by 5.2, the distance it travels, I get 183.456, which is right here. It is answer choice D, 183.5.
183.5.
Okay, the most common wrong answer here appears to have been C, but it looks like y'all were randomly guessing on this one. They were pretty evenly distributed, so if you missed it, that might be why. And if you got it right, it might be also due to random guessing. So if you're lifting something, use the weight. Okay, so number 8 should have been D. All right, number 9. Number 9 says, the graph below shows the force exerted on a ball falling with negative velocity as it is caught in a net. What is the change in kinetic energy of the ball as it moves for 24 meters? So they're telling me, hey, this thing is falling this way. It says negative velocity. But then they're telling me that the force is positive according to this graph. So that means my acceleration is positive. Okay, so I do know that this thing is going to slow down. So my change in kinetic energy here, and they didn't even give me one with the sign on it. So they're just technically this should be negative. I guess they're just looking for magnitude here. But the change in kinetic energy we can find because this is a force displacement graph, and work equals force times displacement, or delta x, it's d. Okay, and so you have that equation, and we know that work is also equal to change in kinetic energy. Okay, so that means if we can find the work from this graph, we can find the change in kinetic energy. As a reminder, if you have a force position graph or a force displacement graph, which this is, we are multiplying our axes together, which means you need to find the area. So the area of this type of graph will give me the work, and the work will be equal to the change in kinetic energy. Okay, so we're just going to find the area for the entire graph because it says for the whole 24 meters. Do double check that. Sometimes I don't ask for the whole graph, so make sure that you read the question carefully. Okay, in order to find the area, I'm going to break this into regular shapes. I have a triangle here, and I have a rectangle here. Okay, so we need to find the area of each and add them together. The formula for area of a triangle is 1/2 base times height. Okay, so we're going to do 1/2. The base of that triangle is 12, and the height of that triangle is 42. So we'll do 6 times 42, which is 252.
Hold on, so like 1/2.
All right, and then we're going to find the area of this rectangle, length times width. Across the bottom from 12 to 24, that is 12. And then again, going up, that is 42. Okay, so again, that's how you find the area of your rectangle. Again, 12 times 42 is equal to 504.
Wait, man.
And then I'll answer your question later on. And then you're going to add them together. Okay, you're just finding the areas and then adding them together. Okay, so 504 plus 252 is 756. Okay, and so that would be your answer is 756 joules. It is the area under that graph, and it is answer choice B for number 9. Technically, this change in kinetic energy should be negative. We just didn't put the sign on there, so it really should say magnitude, but none of them are negative. I need you to sit down. Okay.
Okay.
All right, so number 10. Yeah, I'll take it.
Did you say 756? Something?
Yes.
Oh, I forgot to fill out my ID.
Go ahead. Okay, number 10 says the following graph displays the work versus time of a small motor on a toy car. What is the average power of the motor from 0 to 4 seconds? So this one, like the last graph, I said make sure you read it because sometimes it's not the whole graph. This one isn't the whole graph. It's asking only from 0 to 4. Okay, so in case that matters, make sure that you read it. All right, so this is a work time graph. Again, we're trying to find power, and the equation for power is work over time, which means it is my y-axis over my x-axis. It is rise over run, which means if you have a work time graph, you can find power by finding the slope. Anytime you divide your y-axis by your x-axis, find slope. Power is the slope of this graph. Since the slope is the same the whole time, it doesn't actually matter that we're only looking at the first 4 seconds. You're going to get the same slope if you looked at the whole thing too. But you need to find the slope. Each second, it looks like it's going up by 10. Again, it goes 10 in 1 second, and then 20 in 2 seconds, and then 30 in 3 seconds, and so on and so forth. But you can do rise over run, pick 2 points, and find it. But you're going to get a slope of 10. Okay, and so the power, the average power of this motor is going to be 10 watts, which is answer choice C for number 10. And 84% of you guys got this right, so most of you were able to figure that one out.
Wait, I have to write this down.
You're going to have to get it after the fact then, because we have to keep going. We got to get through this whole thing.
You said 10.
It's 10.
Equals 10.
All right, number 11. Okay, number 11 is one of the most missed problems. It's not the most missed, it looks like it's the third most missed. So this is one that a lot of people had problems with. So listen up, because only 42% of you guys got this right, so over half of you missed it. The question says, during a physics lab, Jack and Jill ran up a hill. Jack is 4 times as massive as Jill, yet Jill ascends the same distance in half the time. Who did the most work? Who did the most power? That's basically what this is asking. Okay, again, the equation for work is force times distance. Okay, and when you're climbing, your work, or your force is your weight. Okay, so the fact that Jack has weighs 4 times as much, if he has 4 times the mass, he's going to weigh 4 times as much, means that he has a greater force, and thus he will have more work because they're going the same distance. So Jack has more work. Okay, so I know it's either A or D. Okay, now looking at the power is work over time. So Jack has more work. Specifically, he has 4 times more work. But it does say Jill goes that distance in half the time. Okay, which if she goes half the time, that means that's a factor of 2 times for the power, but he's got a factor of 4. So he still has more power than her. She would have to have done it in 1/4 the amount of time in order for them to have the same amount of power. Okay, if she had done it in 1/4 the time, they would have the same power, but she only did it in half the time, so this factor is bigger. So Jack also has the most power. Jack, which is answer choice D for number 11. All right, number 12. Number 12, almost everybody got right. 96% of you got number 12 correct. It says, the Incredible Hulk pushes on a wall with 50,000 newtons of force and the wall does not move. How much work does he do? Guys, you have to have 2 things in order for work to occur. You have to have displacement. That's one of the things. So if it says does not move, it's going to be 0. Okay, you have to have that displacement, and you also have to have the force parallel, or at least some portion of the force has to be parallel to that displacement. If it's perpendicular, that's also not work. So remember, you have to have motion, and you have to have a portion of your force, or all of your force, parallel to your displacement. Otherwise, it's not work. This one should be A for number 12. And as I said, 96% of you got it right. There were only a handful of people that missed it. But if that's you, make a note. Number 13, I needed to get to this one. That's why we've been trying to get through this. Your FRQ looks like number 13. So if you didn't know how to do number 13, that this would be a good one for you to copy down. It's not the same, but it is similar concepts, okay? So number 13 says, which by the way, number 13, only 43% of you got right, so you should probably be writing this down. It says, Napoleon has a mass, M, of 100 kilograms. He jumps out of a plane and pulls his parachute. At the same time he pulls his parachute, he has 2,000 meters to reach the ground. The air resistance against the parachute is 800 newtons. What was the net work done on Napoleon as he descends to the ground? So in order for me to get net work, I need to be able to look at the different forces that are acting on him and get my net force, or I need to figure out how much work each of these different forces does. Okay, so if you're analyzing forces, I would very strongly recommend that you draw a free body diagram. Okay, so that's what I'm going to do. I'm going to draw a free body diagram to help me analyze this problem, and you should too. All right, so, sorry, it's out of focus. Go back. So if this is Napoleon, okay, then the forces acting on him, it tells me that the parachute, the air resistance, if he's falling, air resistance is up. It's very similar to friction, except it's with air molecules instead of a surface. It's always opposite the direction of motion. He's falling, air resistance will be up, and it is 800 newtons. That's his air resistance. Okay, the downward force that's causing him to fall is his weight. Again, if you have vertical motion, if you're lifting something or if you're falling, that downward force is your weight. Again, weight is mass times gravity on Earth. We know Napoleon's mass from the question is 100 kilograms, so it's 100 times 9.8, which is 980 newtons. If you weren't sure which arrow to draw longer, now you are. FG should be longer than F air, because 980 is bigger than 800. Okay, so now we've got it drawn correctly. with those two forces. There's no other forces to consider. Nothing's happening horizontally. So if you're trying to find net work, you've got two options. You're welcome to figure out how much work is done by the air resistance and how much work is done by gravity. That's fine, and then you can get the net work from there. But a faster way would be just to get the net force. And with the net force, find the net work. Then you don't have to do it twice and then subtract. Instead, do the subtraction at the beginning and then just do one calculation. That's what I would do. So F net here, my net force here, because this is 800 up and this is 980 down, my net force is negative 180 newtons, or 180 newtons downward because this is bigger than that. You're welcome to write 800 plus negative 980. Again, net force is the sum of your forces. I'm calling this one negative, and I'm calling this one positive. Okay, so that's how I got this. From this net force, I can find net work. Okay, all I have to do to get net work is F net times distance times an angle. If I have one, I don't have one, it's 0. Okay, so I'm going to take my negative 180. I'm going to multiply it by the distance to the ground, which is 2,000. My units are already correct. I've got meters and I've got newtons. So I'm just going to do negative 180 times 2,000. When you do that, you get negative 360,000, which is answer choice. Oh, sorry, hold on. Network. Oh, sorry, hold on. The distance is down. I forgot. They're both negative. Again, his displacement is down. Sorry about that. Okay, so because his displacement is down, he's falling. That should be a negative. So it will be a positive number. It will be specifically positive 360,000. If you'd done it the way I did, you would have caught it as soon as you did it and been like, this is not right. Okay, sorry about that. Pay attention to the direction of your displacement as well. All I paid attention to was my force. All right, so number 13 should be B. It is positive work because his displacement and his net force are in the same direction. Okay, net force and displacement in the same direction is positive work. Again, that's answer choice B. And like I said, 43% of you got that one right. Okay, again, that's very similar to your FRQ, so look at questions like that. You may have some in your problem sets as well if you go back and look at those. Or in the mixed or unit summary. Okay, number 14. Number 14 says, in which scenario is negative work being done by the student on the box? We've got some different actions here. It says, a student raises a box over their head. If you're raising the box over your head, your force is upward and so is your displacement. And if they're in the same direction, that's not negative, that's positive work, so it can't be A. Answer choice B says a student lowers a box from over their head to the ground. If you're lowering a box, your force on the box is still upward. You're still supporting its weight. So you have an upward force because you're supporting the weight of the box, and yet you have downward displacement. They're in opposite directions. That looks like it's our answer, but let's keep reading just in case. Answer choice C says they push the box to the right and it moves right. My force and my displacement are the same direction. That's not it. The last one says a student pushes the box left and it moves left. My force and my displacement are in the same direction. That's not it. It has to be answer choice B. You need the answer to be the one where your force and your displacement are in opposite directions. That's how you end up with negative work. Okay, so 14 is B. 55% of you got that right. That's a lot lower than I would expect. You will see a question like this on your test. Okay, so look over it if you need to. All right, number 15. Number 15 says, in a scrimmage against his players, a soccer coach at Bridgeland High School scored a goal. If the coach uses 1,150 newtons of force to run and he traveled 12 meters to the ball at a speed of 9.2 meters per second, how much power was needed for him to score? Again, the power equation is work over time. If you know work and time, you can use that equation. But when I read this, I don't actually know work and time. I can find out what the work is, but I don't have a time in here. However, if you recall, I also showed you another equation you could use for power. And I told you you're going to need this. It's not on your formula chart, though. If you substitute in for work, the equation for work, force times distance, and you put that over time, We saw this in the notes. What is this? Velocity. You can rewrite the power equation to be force times velocity. That's the equation you need to use because that's the information you have. Okay, so because this is velocity, this is also an acceptable equation for power, and it's the one we have to use here. Okay, so you'll have to do that on your own if it shows up on the test. You had to do it here. So we're going to take our force, which is 1150, and we're going to multiply it by his velocity, which is 9.2. And that gives us our answer, 10,580, which is answer choice C.
Wait, 1150, so.
10,580. All right. 70% of you guys got that right, so it looks like y'all remembered that, or at least most people did. But if you forgot, again, make a note. One question left, number 16, and it's one that you guys did pretty good on. 83% of you got number 16 right. It says, an experiment is conducted in which the motion of two identical objects is measured using a motion detector. The data collected is plotted in the two position time graphs shown below, which correctly describes the net work and the change in kinetic energy experienced by each. This also is similar to something that's going to be on your FRQ. Okay, so when we look at this, I clearly have two graphs that both show acceleration. Okay, they both show a change in velocity because this is an XT graph and it has a curve on it. Again, VT graph, different. You could see that too. You might want to review that if you don't remember. But your VT graphs will look different, but you could still answer this question with two VT graphs, okay, if they had given you that. The slope on an XT graph, the slope is the velocity. Okay, so this one has a smaller slope and is thus slower. This one has a much steeper slope and is thus faster. Y'all agree? Okay, which is going to help us here because we're looking for the greater change in kinetic energy. I want to know how fast they're going. Okay, so this one very clearly will have a greater change in kinetic energy because they both started out at rest, and this one's faster at the end, so it's going to have a greater change. So which one's greater? I know that ball B has to have greater change in KE, so if I look at this part, I can eliminate two of my choices right off the bat. Okay, but the other thing I need to look at is greater net work. But guys, net work equals change in kinetic energy. So if it has a greater change in kinetic energy, it's also a greater net work, which means if this one has more change in kinetic energy, it also has more work. And so it should be ball B for both, which is answer choice C for number 16. And as I said, 83% of you got that right. All right, guys, the test tomorrow, the multiple choice section will look pretty similar. Okay, it's not going to be identical, it never is, but they usually look pretty similar. And I'm telling you what your free response is going to at least kind of look like. So make sure that you look at those types of problems. Again, I did record this. This video will be available online, so you're welcome to check back later today when you get home. If you want to go through the quiz again, it'll be in the YouTube playlist. Also in that YouTube playlist are problems that I worked through from all of your problem sets. So if you got stuck on any of those, or if any of the questions in the problem set were similar to the ones that I said, hey, look at these, then those might be good videos to watch as well. Okay, but you do have a test tomorrow. If your quiz grade wasn't so hot, do the unit summary. It is a redo. So if you got a 50, do the unit summary and change it to a 70. Okay? So keep that in mind as well. It's also great review even if you did well on the quiz. I'd still recommend the unit summary for the extra practice.